All right, hi everyone. So we're jumping into this video in the middle of a lesson that we started talking about arc length with. We decided that we could find arc length pretty simply by taking r times theta. And the conversation was just starting to move into angular speed and linear speed when we had to go. So let's bring that conversation back to the front. So just a reminder here that the angular speed, which we call omega, can be found by taking the angle of rotation in radians divided by time. That omega, angular speed, equals theta over t. Then we started to talk about linear speed. And I want to just change something here as we get going. I just double checked to be consistent with the textbook problems that we use. They don't use an L for linear speed, they use a V, so I want to be consistent. So what was our development here? Distance equals rate times time. We've known that relationship for a long time. While when we're talking about a point traveling along an arc, our distance is actually our arc length, which is s. So s, the arc length, which is a distance, is equal to, I'm going to change this again back to a v, is the velocity, the linear speed times time. Distance equals rate times time, so the arc length is equal to the linear speed times the time. Well, if we solve that for v, the linear speed, is going to be the arc length divided by the time. That makes sense. It's still distance, arc length, divided by the time is our linear speed. Now, we also recalled that arc length then is equal to r times theta. That's how we found arc length. We said that earlier. Arc length is equal to r times theta. So the linear speed is equal to r times theta over t. But then recognizing that theta divided by t looks familiar, look up there. That's the angular speed. So the linear speed, the velocity, which is in a distance per time, is equal to r times the angular speed, the radius, times how fast that angle is changing. So find the angular speed of the minute hand of a clock in radians per minute. All right, we're talking angular speed. This is our omega. Let's see, how does that go again? Omega is equal to the angle of rotation divided by the time. So, we're talking about the minute hand of a clock. Well, I want to figure out that in radians per minute. Well, what do we know about the minute hand of a clock? Do we know an angle and a time that corresponds with that minute hand of the clock? Yeah, we do. We know that that minute hand goes all the way around the clock in 60 minutes, doesn't it? Well, what's that angle of rotation when we go all the way around the clock? That is an angle of 2 pi radians. Over, how long does it take to do that? Now, we know it takes 1 hour, but we want radians per minute, so this is in 60 minutes. So the angular speed is 2 pi radians over 60 minutes. We know that would reduce to pi over 30 radians per minute. Okay, does that make sense? Pi over 30 radians per minute. Well, after 30 minutes, how far would it go? It goes pi over 30 each minute. So for 30 minutes, it's going to go 30 pi over 30, which is just pi. So in 30 minutes, half an hour, it's gone pi radians, halfway around the circle. That makes sense. Okay? If I multiply it by 60 minutes, 60 pi divided by 30 is 2 pi. It's the angle of rotation all the way around the clock. There we go. Number 2. A hard disk in a computer rotates at 3,600 revolutions per minute. Find the angular speed of the disk in radians per second. All right, still with angular speed. Theta divided by time. Well, we're traveling 3,600 revolutions per minute. What is our angle? I know that the denominator here is 1 minute. What's the angle that it travels in 3,600 revolutions? Well, what do I know about one revolution? That's one time around the circle, isn't it? Okay, that is 2 pi radians. Oops, I missed a 6 in there, didn't I? There we go. 3,600 revolutions. Well, each revolution is 2 pi. This makes sense here. This is, well, 3,600 times 2, 7,200 pi radians. So we're going to take 72, let me change the color there, 7,200 pi radians per minute. Well, I want radians per second, so I'm going to take this and change my 1 minute into 60 seconds. And let's see if I can reduce that. 7,200 divisible by 60, 120. 120 pi radians per second. All right, so just working that we can switch between our units. I'm checking that we understand what revolutions are. All of that looks good. Let's go to number 3. A wheel on a bicycle has a radius of 12 inches. The bicycle wheel is rotating at 140 revolutions per minute. Find the speed of the bicycle to the nearest mile per hour. Speed of the bicycle. What am I looking for here? Am I looking for the angular speed? No, I'm not. I am looking for the linear speed. Linear speed equals, well, we've got some options. We can take the arc length divided by the time. Take the radius times the angle divided by time. Or we can take the radius times the angular speed. Well, I'm going to take the radius times the angular speed because I know the radius of the bike. Now I just have to figure out the angular speed. How do we find angular speed again? Our angle divided by the time is rotating 140 revolutions per minute. What is that angle? 140 revolutions per minute. Sounds familiar. Here it was 3,600 revolutions per minute. How did we figure out what our angle was? We took the number of revolutions times 2 pi. So that would be what? If I take 140 times 2 pi, I get 280 pi radians. Over per minute, 1 minute. There's our angular speed. So now to find our linear speed, I'm going to take the radius 12 times the angular speed, 280 pi over 1. And I get 12 times 280, 3360 pi. What are my units on that? Well, that is in inches. This was in minutes, so we got 3,360 pi inches per minute. Now I want this in what? Miles per hour. We're going to have to do a little converting. I'm going to keep my multiplying going. A little unit analysis. What should we change first? Inches into miles, minutes into hours. Doesn't matter to me. Let's go minutes into hours. I need minutes to cancel out. I need hours. What do I know about minutes and hours? 1 hour is 60 minutes. Boom. Now let's change inches into miles. I need inches to cancel. I need to have miles. What do I know about inches and miles? Well, 1 mile is how many inches? Well, 1 mile is 5,280 feet. 1 foot is 12 inches. I'm going to take 5,280 times 12. 63360 inches. And there we go. Now, this is, I'm going to multiply out here. It's going to have a pi in it. I want something a little bit easier for me to understand, so I'm going to approximate. I'm going to multiply my numerator, 3,360 pi times 60. I'm going to divide it by our denominator. Here we go. And I get about, well, this is really close to 10, about 10.0 miles per hour. Is that reasonable? If the bicycle is traveling, has a radius of 12 inches for the wheel and going 140 revolutions per minute, does that make sense? Okay, so this is a very algebraic way here to go through this. Let me just use another approach just to check to make sure this is a little bit easier. Can I figure out how far it goes in 1 minute? Let me figure out how far it goes in 1 minute. Well, it goes 140 revolutions per minute. I abbreviate that RPMs. Well, each revolution, you know what, I'm not going to do that. I'm going to say revolution per 1 minute. I'm going to multiply that by 1 revolution how far does it travel? Well, it travels a distance equal to the circumference, which is 2 pi times 12. And that is in what units? 12 inches. So really, I've got 140 times 24 pi. I have 3,360 pi inches per minute. Man, that number's looking familiar. Oh, look at that. See, I just want to show that there's a lot of different ways to think through it. Sometimes we get really stuck using formulas, but hopefully we can reason through it in different ways. It goes 3,360 pi inches per minute. Just to give that a little perspective, that's about 10,556 inches per minute. Well, how many feet is that? That's 879 feet, roughly, I'm rounding, per minute. Okay. Does it make sense that we're going about 10 miles per hour? Well, an hour is 60 minutes. If I multiply that 879 by 60, I get about 5,270 or 52,778 feet. That's roughly how far I've traveled in an hour. How many miles is that? If I divide by 5,280, we can see it's about 10 miles. So yeah, we got the right answer. Just showing you different ways to work through it here. We tend to like formulas. I like formulas. I always have liked that. But sometimes we don't really need a formula if we can reason through it, understanding our units. Okay. We were about 10 miles an hour. Well, thanks for tuning in today. I appreciate it. Hopefully your head is not spinning too much. If it is, ask questions when I see you again. Thanks for tuning in.